we're gonna finish off lesson 5. I'm gonna give you a bunch of homework. I'm gonna start lesson 6 and get partway through it, and then I'll give you some time in class. So I like example 6. I like example 6. I like example 6. Here we go. It says this: a satellite has an orbital altitude. Oh, don't give me any altitude. No, that's don't give me any attitude. Altitude is this number right here. That's the altitude. What I want is the orbital radius. In fact, part A says, what is the orbital radius? And usually I call that our orb. As a picture, Vikas, what that is this number. How the heck, if I know the altitude, how can I figure out the orbital radius? How far I am from the center of the planet? Okay, add the Earth's. Or if I'm altitude above the moon, add the moon's radius. Or if I'm in orbit about the sun, add the sun. Read the questions carefully in the homework. Sometimes I put you around the moon just for giggles, right? So the orbital radius is going to be, let's write it in our notes as r Earth plus altitude, just so that we know what the heck we did. And it's going to be 6.38. I'm going from memory. Is it times 10 to the 6th? That's the Earth? Yeah. Plus, and the altitude is 1.2 times 10 to the 6th. Hey, are both these 10 to the 6th? Then really, it's going to be 6.38 plus 1.2. 7.387. I think it double check me, but I'm pretty sure it's going to be 7.58 times 10 to the 6th meters. So I'll flip-flop on your test and in the homework. Sometimes, Alex, I'll give you the orbital radius. Yay! Great. Easy. Sometimes I'll give you the height or the altitude. Okay, add the planet to it before you start. Read the question carefully. Don't always assume you have to add the planet. Read the question carefully. Kevin, what does B want me to find?
What is its orbital velocity?
By the way, someone pointed out to me in my other class, Mr. Duick, you really mean orbital speed because there's no direction. You're right, the direction is tangent to the radius, but that's always changing. I'll change that next year. But for now, did you say orbit? Gravity is what's pulling me in a circle. Hey, Dale, what's C asking me to find?
Orbital period.
Did you say orbit?
Yep.
You know what I'm going to do? I think I gave you the whole page, and there's 2 parts remaining. I'm going to just go like that. And I'll do part C here. Gravity is what's pulling me in a circle, just so you can see how they slowly morph it and flow out. Kevin, gravity doesn't change. Universal gravity. What's my equation for universal gravity? Big G.
Over big G.
Little m over, and that equals m. Oh, you said orbital speed. I'll use v squared over r. As opposed to Dale's, where I'm going to go big G, big M, little m over r squared equals m. What am I going to write here, Dale?
4 pi squared r over 2 squared.
Okay. Mitch? Once you get the satellite up there, the mass is irrelevant. Now, you're going to notice in today's lesson, when we look at how much energy it takes to put it up there, the little m won't cancel because it takes way more energy to put the space shuttle up there than it does to put a little tiny communication satellite up there. It does. But in orbit, once you're up there, yay, mass cancels. Kevin, in B, does an R cancel? Because that R would move to the top and cancel with that one. Does an R cancel, Dale, in part C? No, and a common mistake. Kids want to say, doesn't this R cancel? And unfortunately, then you botched everything for the rest of the question. This R is going to move up to, R squared is going to move up to there and give you an R cubed. Okay. Kev, what am I trying to get by itself?
You're trying to get B by itself?
Oh, how would I do that?
You would
Just square root.
Yeah.
I gave you the easy one because, you know, you're not too... Oh, I gave you the easy one. And Dustin, this is the equation that I think we put on the box way back on page 1. And I've told you, I mean, if you want to memorize it, I guess you can. I've just never bothered because 2 lines and I'm there. Kevin, what are we trying to get by itself in your equation? Oh, sorry, Dale. I said Kevin. Dale, what am I trying to get by itself in your equation?
The T.
Ugh. Well, no. Is this 1 fraction equals 1 fraction? Well, then stuff moves diagonally. I'm going to move the t squared to the top. I'm going to move the r squared over to here. It's going to become an r cubed. And the big G, big M is going to move to the bottom. If you want to draw those in, you can. If you can just see it, great. But I think I'm going to get, Dale, t squared equals 4, yes? Pi squared r cubed over big G, big M. And now I've reduced this to the level of difficulty that even Kevin can handle, because how would I get rid of the squared? Do I need to cube root this time? No, we did notice that if I wanted to get the r by itself, I actually had to pull cube root out of my back pocket. And it was kind of with a bit of a nerdy smile. Holy smokes, I'm actually using cube root, and it's useful for a change, not just something that my math teacher showed me. Okay, now it's plug and chug. Orbital speed is going to be 6.67 times 10 to the negative 11. A number of you have shown me that you have that number on your calculator as a constant programmable. Great. Mass of the Earth, 5.98 times 10 to the 24th, I think. All over, what was R? 7.58 times 10 to the 6th. If we want to stay in orbit, how fast will we need to be going? 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, divided by 7.58 times 10 to the 6th. Square root of that. That seems about right. You might recall we actually calculated the speed if you wanted to orbit right at the Earth's surface, and it was, I think it was like right around 8,000, it was 8 kilometers a second, I think. As you go further out, you don't have to go as fast. In other words, as r gets bigger, what happens to your orbital speed? Gets bigger, gets smaller. As it gets smaller, if you want to be technical, gets smaller by the square root of 1 over r. Hey, those, who's in calculus here? As r approaches infinity, how fast do you need to go? If you're out at the edge of the universe, how fast do you need to be traveling to stay out there? Where's the r, on the top or on the bottom? That's gravity, but not what we're talking about here. If you take the limit as r approaches infinity, v is 0. In other words, if you're at the edge of the universe, there's no gravity, you don't have to be moving, and you'll still float there just fine. Thank you very much. Oh yeah, that makes sense, but sneaking in some calculus here. I got, what was it? 7.25 times 10 to the third? How much kinetic energy would this satellite have? Well, a half times m, the mass of the satellite, which I don't think I gave you in this question, but then the mass wouldn't cancel, times that v squared. Period. How long will it take to orbit the Earth? Well, this is longer, but not much uglier. 4 pi squared 7.58 times 10 to the 6th cubed. Again, I strongly encourage you, practice typing these in on your calculator. In particular, You want to find out things like where do you or don't you need brackets. I think I can go 4 pi squared times 7.58 times 10 to the 6th on 10 to the, I've learned on, geez, Duke, to the 6th cubed. I've learned on my calculator an exponent next to scientific notation. My calculator knows that I want to cube this whole thing, not just the 10 to the 6th. You might need to put the scientific notation thing in brackets on your calculator. I don't know. Divided by, I have more than one number on the bottom. You better put it in brackets. Is that right, Mr. Duke? Looks good. Square root of that. And I get 6565.5. To 3 sig figs, 6, 5. Will the 6 stay a 6 or become a 7? Okay, so the period is 6.57. Was that what I said, Mr. Duke? Yep. Times 10 to the 3rd seconds. Or if you want to put it, I'll divide by 60. Every 109.4 minutes. Goes around the Earth roughly a little under every 2 hours. Okay. Again, the point is, any one of the 3, you can find the other 2. So, what's your homework? I already gave you number 1. I skipped 2. I said 3, 4, 5, 6, 7, 9. Oh, I already gave you 12, 13, and 14. Yeah, the homework hasn't changed. 10 is tricky. Okay. I'm not going to give you the rest of class to work on this, though. I'm going to start the next lesson, and then I'll give you about 20 minutes at the end of class to work on this, okay? Lesson 6. Orbital potential energy. Or how much gas do you need to get to there? Now, so far, we used to say this. Potential energy was equal to, and what equation did we write? Yep, you're right. Say it loud. There's a problem with this equation when we go cosmic. What's G? It's only 9.8 on the Earth. As you go further from the Earth, what happens to this value? So we need to, if we're going to go cosmic, we can't use that equation. We need to toss it. If I'm still on the Earth and I'm doing is change in height, change in speed, curvy path, like earlier this year, like some of you just recently did in the homework that you finally handed in, then we can use MGH. But if I'm talking about orbits and outer space, here is the new one. Are you ready? In fact, we're going to have to get it by going graphical. I wrote down here, recall the area under a force versus distance graph work. I'm going to go even more fussy. If I call this x1 and if I call this x2, the work required to move from x1 to x2. Can you see now I've got a position in my analogy that might take care of the whole moving from the Earth's surface to a weaker gravitational field? Okay. For the force of gravity versus separation distance r, so now if we go cosmic, first of all, the graph looks a bit different. The graph looks like this. For those of you in Math 12, it's the reciprocal of a parabola because the gravitational equation has an r squared in it, but it's an r 1 over r squared. It's the reciprocal of a parabola. I think you guys have done reciprocal functions in Math 12 now a little bit, yeah? Or you're doing it right now? Okay. So, if I have a position R1 and I have a position R2. That area there is going to be how much work it takes to move from R1 to R2. Consider. So here is a graph of gravity. Let's put a line right here, and let's call this R Earth. And let's call this R Orb, the orbital radius that we want to reach. This area is the work required. And remember, work, really, you can think energy or fuel required to move from the surface of the Earth to our orb. Now, I picked my words very carefully. I didn't say this is the amount of work to get in orbit. All this does, Clay, is calculate how much work you need to lift yourself up there. Unfortunately, it doesn't keep you moving once you're up there. If this is all we did, as soon as we stop and let you go, you'll come crashing back down to Earth. All of that potential energy will turn into kinetic when you hit the ground. To get into orbit, not only do you have to lift up there, then you have to give yourself just the right kinetic sideways velocity to stay in orbit. Okay? What is this equation? I'm going to do some sloppy, bad math, but it's going to give us the right answer, even though a math university prof would cringe at what I'm about to do. On the next page, since work equals force times distance, we can say this. The potential energy, the work done to move something up, is going to be the force of gravity times distance, except we never use distance in our gravity equation. Since we want to go into orbit, we want to use r's. What do you notice about the r's in this case? They cancel. Now, this is garbage math, okay? Who's in calculus? Have you guys started integrating yet? Okay. In reality, to find the area under a curve, you do something called an integral of this equation here. And if you did an integral of the gravity equation, you get the correct equation that I want. But I can't do that with you. Instead, I'm going to say this. Here it is. The cosmic potential energy equation is equal to, leave a small space because I need to stick something in there in just a second, big G, big M, little m over R. Is that what it says on your formula sheet for PE or for EP in this unit? No. What? Put a negative there. Duick. Yeah. Why negative? Because in calculus, if you do the integral properly, you get a negative in your equation. I can't say that because you guys don't know what integrals are, and only a few of you are calculus. Okay. Why negative? Ready? Here's the Earth. Travis, catch. Here's my little satellite. Okay? No, just stay there. Hold the Earth up. As I move away from the Earth, if I let this go, what does it want to do? fall back down. It wants to lose potential energy. You with me okay on that? In fact, the energy will turn into kinetic energy. All right. What if I went all the way out to the edge of the universe? Right here, where there's no gravity. If I let this go now, if there's no gravity, will it fall? So if it won't fall, how much potential energy does it have as a number? 0. We're going to define 0 to be, and here's the magic phrase, relative to 0 at infinity. However, that must mean for me to get here, for me to get from here to here, I did have to add energy. I had to do work. If I end at 0, but I'm adding energy, what kind of numbers must I be starting with if I can add and end with 0 as an answer? Negative. These are all negative numbers. Okay? The reason there's a negative in my potential energy equation is it turns out if I define 0 to be infinity, this has less energy. What numbers are less than 0? Negatives. A little weird, but it's going to actually work out quite nice. Earth thanks you. Okay? So I wrote down here, why negative? The real reason is it's an integral, and that just works out quite nicely. But for you guys that aren't doing calculus, out at infinity, at the edge of the universe, an object would have no potential energy because it's not in any gravitational field. If you let it go, it won't fall. But you would have to add energy to get it there. You have to burn a lot of fuel to get it there. You would have more energy out there than close to the Earth. You have less energy close to the Earth. If our height is less than infinity, we have less potential energy. What numbers are less than 0? Negatives. So we use the phrase relative to 0 at infinity, or you may even see it abbreviated as relative to Mr. Dewick? 0 at you may see it RTZI in the homework. That's my way of telling you, please use the cosmic potential energy. Don't use MGH. Won't work. Okay? Let's look at stuff dropping from the sky. The sky is falling. The sky is falling. A 3,400 kilogram mass, let's say a satellite that is no longer working properly, is released from a height of 6,300 kilometers above the Earth. How fast will it be going when it hits the ground if we ignore air resistance? Is there a change in height? Yeah. While there isn't a yucky, curvy path, are we cosmic here? Are we in outer space? This is a job for conservation of energy, but we're going to use the cosmic one. I'm still going to start out by saying remember that, Kohei? We've seen that before. Let's go best case scenario. Let's pretend that this satellite was at rest. Now, in real life, it would have still most of its orbital speed. In real life, it would already have a massive amount of kinetic energy. This is why asteroids and satellites don't have to be very big, and they can still do tremendous damage, like that one that exploded over Russia a few years ago, right? That's not 0. This is not 0. Wait a minute, Mr. Dewick. Isn't our final height 0? That would be for MGH, but relative to 0 at infinity, infinity would be 0, and we're not there. Nothing else, sadly, is going to cancel. This is going to look like this. Negative big G, big M, little m over R initial. That's what initial potential energy is, cosmically, equals a half little m v final squared. plus negative big G, big M, little m over R final. What's this question asking us to find? Yeah, V. Oh, does the speed that it hits depend on the mass of the satellite? No. The damage that it does depends on the mass of the satellite, but that's not what this question asked. It turns out there is a little m there, a little m there, and a little m there. And I'm going to, Josh, I think, plus that to that side, because it's got a minus in front of it. So, negative big G, big M over R initial plus big G, big M over R final. That equals 0.5 VF squared. I could get rid of the 0.5 by going, don't write this down, times by 2, times by 2, times by 2. No matter what, this is going to be complicated enough that probably I'm going to crunch this, eraser, that was bad, crunch this whole side on my calculator, get an answer, hit equals, and then I'll go divide by 0.5 square root. Looks like I accidentally erased the equal sign. Oops. Is that okay? How much room did I have? Oh, a bit more. Negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. So this is about my limit for trying to get the V by itself. I might just crunch the left-hand side and then get the V by itself. What's the initial radius that we're at? Read the question. Did they tell me the initial radius that we're at? What did they tell me, Clay? In what units? Okay, so my initial radius is going to be the radius of the Earth, 6.38 times 10 to the 6, plus well, 6,300 kilometers times 1,000. 6.3 times 10 to the 6th. Is that right? Clay, question?
How far away is 6,300 kilometers?
The ISS orbits at about 150 to 200 kilometers. A fair ways away. Okay. This is going to hit the ground pretty fast. You would not want to be near this thing, especially with the mass that I gave it. That's a decent-sized communication satellite hitting the ground. Now, Mr. Duke, wouldn't it burn up in the... I'm ignoring air resistance. Yes, in actuality, it'd probably start to burn up in the atmosphere, and there'd be all that, but that's beyond our ability to deal with. We said air resistance is a pretty yucky force. There's my initial potential energy. Plus 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What's my final radius? Oh. Yeah. 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 No, because G is changing. That's the problem. This distance is so big that the gravitational field is not going to be constant all the way through. And so unfortunately, the only way this equation works is if we define 0 to be out at infinity. I wish we could. There's just no real short way to do this. Since we're going realistic, yeah. Sorry?
And R up if we do it, and then this thing will go from there. If we divide by zero.
What you're really saying is, Mr. Dewick, what would happen if we had a singularity? What you're actually talking about, by the way, is yes and no. Okay? Can I come back to your question in a second? Can we finish this? Okay? Make sure I don't forget your question. Have I gone on a rant about how it's useful to have a good calculator? Have I? Okay, I want all of you to follow me character for character, because this is a lot of typing. And this is enough typing, Jason, that we've just introduced a good chance of a screw-up, of an error. So here is maximum bang for minimum buck. I go like this. Negative. First term. I go like this, 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. Mr. Derek, you haven't done it. Just wait. Divided by, is there more than one thing in the denominator of the first fraction? Yeah? So what am I better do with the denominator? Put it in. Okay. What's the radius of the Earth? 6.38 times 10 to the 6th plus 6.3 times 10 to the 6th. And I stop here. Wait a minute, Mr. Dewick, there's more to just make sure you've typed that in correctly. Make very sure you've typed that in correctly. Be really careful on your first time. Clay, you're looking puzzled.
I can't read it.
Okay. Koei, is that okay? It's got them in front of you, too, people.
Yeah, I can see the top row, but I can't see the bottom.
No, I mean, you have the it's
Yeah, I can't read that either.
oh,
It's not ready.
our Earth plus 6.3 times 10 to the 6th. Okay. Oh, Kohei and Clay, I got a couple desks right there. If you're really having trouble, feel free to move up. No, it is, but that's okay. You guys with me? You got them typed in? Here's what I'm going to do. I'm going to hit equals. And I'm going to carry 5 or 6 sig figs. I'm going to write negative 3. In this case, I'm going to write negative 3145639 right here. Negative 3145630. 3145639. Top row, big G times mass of the Earth, 6.67 times 10 to the negative 11 times big M, 5.98 times 10 to the 24th. Okay? Those of you that can't read, I got to move on here. I want to get this. You okay with me so far, Jason? Here's what I want you to notice. In the second fraction, isn't everything identical except you don't have that number there? This is why I went on my rant about getting a good calculator. Hopefully you can just backspace. If you have that back arrow button, delete the negative. Delete the, and I would argue that's way less typing than retyping that whole mess again. Yeah? I'll carry that to a bunch of sig figs too. 6251818 Positive 6251818 That equals 0.5 V final squared. Mitchell, that's the way to get this with the least amount of typing. Otherwise, you're going to find you're almost always typing big G twice, typing the mass of the Earth twice, and those are lots of things to type, and you're introducing the chance of making a typo. Is that okay? Everybody got the same thing as me for the two numbers? Okay, if you didn't, you need to practice this. But now, how can I combine the left side into one number? And here's the nice thing. I have this second number stored on my calculator already, do I not? So I'm actually just going to go like this. That number, take away 3145609. 314 5609. 314. I missed a number, thank goodness. 56309. Yeah? That equals 0.5 V final squared. Now what? How would I get the V final by itself? Not yet. What else is in front of the V?
0.5.
So how do I move that 0.5 over? Divide by 0.5, square root. I've played around with this, Alex, quite a bit. That's about the least amount of typing to get to this answer. It's going to hit the ground pretty fast, almost 8 kilometers a second. It'll be hauling. 7,800, I'll go to 3 sig figs. V equals 7,880. What's your question?
How long do you think you would see that for?
How long would you see that for?
Yeah, if it didn't like light up with the air resistance, like just if you could like see it.
If it was traveling, first of all, it depends how high it's traveling, because the higher it is, the further things are away from you, the slower they seem to move, right? You've noticed that, things on the horizon, cars on the horizon seem to be moving very, very slow, okay? But if you're saying if it was a few hundred meters up, it'd probably be visible maybe 2 seconds, maybe. About like that, probably. You wouldn't be a happy camper being near it when it blew up.
Yeah, I was gonna say.
It'd get your attention.
Once in a lifetime experience.
It would be, but it might be an end of a lifetime experience. Okay. This is the cosmic potential energy equation.
And we will pause here.
Okay.
Oh, that was
I think what we're going to do is this. Turns out what I've just showed you is actually the physics of building a Death Star. Say what? Put your pencils down, look up.